Sent. Take it away.
Okay. Hi, everyone. Thank you for the organizers. It's great to have an in-person conference, and thanks for the invitation to speak. So I'm going to talk about some joint work with Gerard Benarous and Akash Jagannath on stochastic gradient descent and first-order methods for kind of simple problems of parameter estimation in high dimensions. So the general framework that we're going to be thinking about is, so you have a family of probability distributions P sub theta, and theta is in Rn, so my parameter space is n-dimensional and n is large. And I'm going to get m IID samples from P sub theta naught. So there's some like hidden or true parameter theta naught, and I'm getting IID samples from that. And the estimation task is, of course, to produce an estimator that attains, let's say, 1 minus little o of 1 correlation with theta naught, or essentially recovers theta naught. Okay. So this is a pretty general framework, and some simple examples that fit into it that we've heard people talking about over the past couple of days are, for instance, the first one here is tensor PCA. So you get some Gaussian K-tensor IID entries, and it's spiked by some rank 1 perturbation. So in this case, it's going to be exactly the hidden parameter is the vector that you raise to the tensor power like k. And maybe there's some signal to noise parameter here, or that can be absorbed into the number of samples. Another situation that you might think about is you have some kind of like a single layer network or like a teacher-student framework where you have an activation function f. You're given a projection, so you get to take projections with, let's say, Gaussian feature vectors of the hidden parameter theta naught. You run it through some nonlinear activation f, and maybe there's some additive noise. And so what you're seeing are, I don't know what that is. So what you're seeing are IID things like this, where the randomness is over both a and epsilon. Another framework you can think about is like a mixture of two Gaussians, let's say. So here eta is just a plus minus 1 with probability half-half, let's say. And so you either get theta naught plus some centered Gaussian or minus theta naught plus some centered Gaussian. And you're trying to recover this vector theta naught. Okay, so pretty general framework. And what we're aiming to understand is, let's say, algorithmic thresholds using some kind of first order method. So a general approach to these kinds of problems is to have some kind of a loss function, let's say a mean squared error or a log likelihood or something. And the best estimator given such a loss function for generalization, for instance, is to take the minimizer of the expectation of the loss, where the expectation is over the y. So you want to have some algorithmic method for outputting this x. And a common algorithmic approach is to minimize the empirical risk. So you take this running average over your losses for the MIID data points that you got. And this ends up being, so this is a fairly high dimension, this is a function in Rn. And oftentimes it can be pretty complex in the sense that it has lots of minima, maybe exponentially many in the dimension, in the ambient dimension. And so optimizing this is a highly non-convex problem, but it's something one could try and do. Okay, using, for instance, a gradient descent or a Langevin dynamic, something like that. So the goal for the talk, or our goal generally, is for maybe simple problems of simple choices of this loss and simple problems in a way that I'll explain later, understand the thresholds in terms of the number of samples. So the m necessary in terms of n needed for first order methods to obtain 1 minus little o of 1 correlation with the hidden vector theta naught when initialized from random initialization. So sometimes spectral initializations can help, but I really want to key in on the role that initializing randomly and just using a first order approach, what does that do for us? And why is that different from when you use something like a spectral initialization? So the kinds of things that I mean by first order methods, well, oh, sorry, before I get there. So there's two kind of well-studied approaches to this, this problem. for instance, you think, let's have in mind gradient flow or Langevin dynamics on R, which is the empirical risk. So one approach to getting thresholds for this problem is mixing times. So for instance, with the Langevin type of thing or an MCMC algorithm, you can understand how long does it take for the algorithm to converge to its stationary distribution from a worst case initialization, okay? And there's a lot of tools for this. You can find some kind of a bottleneck in the landscape, terminology like free energy wells and overlap gap property that we've heard over the last couple of days come up. And a lot of people here have worked on things like this. And so generally the approach is to show that some observable of your system has some kind of bottleneck. So you have to transition from some large mass region to another large mass region through some small mass region. And for your stationary distribution, that's hard. And therefore, from a worst case initialization, it takes exponentially long generally for you to mix. Okay, that's used as an indication of the hardness for an MCMC approach for this. So for instance, you can think of like Jerem's paper for a planted clique as such a thing. But there's not really an indication that random initializations can't somehow avoid these kinds of bottlenecks. And that's a general paradigm that I'm interested in. Another class of approaches does kind of hone in on maybe different kinds of initializations other than worst case. And that's based on taking limiting ODEs, fixed points of limiting ODEs, looking at state evolutions, things like that. So there's a mean field limit, AMP, state evolutions. Generally, these kinds of approaches first send an n to infinity limit and then take time large. And so what that means is these are short time asymptotics. So the success or failure of local algorithms, you can say something about it in order n many steps, sometimes order n log n using some kind of stability arguments, but not beyond that. And so there's a gap between, so these kinds of approaches, maybe you can say something about if you started from a random initialization or from like a nice initialization that you're actually interested in. But the kind of algorithmic obstruction you'd get is that in order one time or in order one in continuous is n in discrete. So in short time, you're not going to be able to get to a reasonable recovery. So there's a whole gap between this kind of time scale or this kind of number of steps and the exponential kinds of things that you get from worst case. And so what I want to talk about is answers to the following two types of questions. So are there situations in which a random initialization really gives you an advantage over a worst case initialization kind of thing? Maybe these kinds of overlap gap properties can even tell you, a worst case initialization within a subset of your space, like where you have even starting near zero correlation, but still it might be that a random initialization does better than the worst point with zero correlation. So that's the first question. And the second is, are intermediate timescales relevant? So is it possible that even though these kind of fixed point approaches kind of get stuck on order one times, if you wait a little longer, like a polynomial in n, you actually are able to do better. So maybe there are problems where it's not either a short time or an exponential kind of trade-off, but there's some polynomial throughout the time scale that's relevant. So with that, I'll talk about, so some of the kinds of first order methods that I'm thinking about generally are gradient descent, where your update is just you take the gradient of your empirical risk. This n is to match the order n versus order one trade-off I was talking about earlier. And you have some step size delta. So you do this kind of just simple gradient descent update. Another option is this Langevin type dynamics where you add some white noise step every time. And maybe what I'll be talking about most for this, for the purposes of this talk, because it's the easiest to analyze, is a stochastic gradient descent algorithm, where instead of optimizing this risk function, you're getting this your data point y, and you're just using a gradient update with that single data point. Okay. So all of these you can do a kind of simple rewriting where you subtract off the generalization error, and So what you'll see is there's this common part to all three of these situations, to all three of these algorithms that I'm talking about, where you just update with the generalization error or the population loss. And then there's some mean zero correction. And this mean zero correction in the online stochastic gradient descent situation is IID. In the other situations, it's not IID, but at a fixed x, it's mean zero. Okay, so generally, you can think of in the small step size limit, you get cancellations from these mean zero terms. And so these algorithms are going to be well approximated by just a kind of dynamics that updates using the mean of your loss function. Okay. Of course, that's a small step size with the dimension fixed and or with time order 1 relative to the ambient dimension. And so while that approximation gives you these kinds of mean field limiting equations, and that's how you get like n to infinity, then time to infinity limits, if you're trying to hone in on time scales that diverge with the dimension, you need to actually care about this perturbative term. Okay, so everything that I'm going to say in the rest of the talk, we're just going to focus on online SGD. In the case of tensor PCA and maybe some other simple examples, we can say some things about gradient descent and Langevin, but it's obviously easier to work with the SGD situation. Okay. So let's focus on this population dynamics, which is
not true that. It's not true that I guess by mean field approaches you refer to iterative approaches like AMP. It's not true that you replace that thing by zero in those approaches.
In AMP, there's an extra correction term.
Well, yeah, I mean, but it's not equivalent. I mean, you can analyze.
But like an ODE limit kind of approach.
Yeah, you're not replacing that. You're not taking the average by zero of this approximation.
Okay.
You're not.
Okay.
I mean, yeah, it's like in the Cogliandolo-Kurchan, you're not replacing that by zero.
But there are situations in which, like if I looked in a fixed dimension limit, then if I looked in fixed dimension and took a delta to zero limit, then I would be doing that.
Fixed dimension, yes.
Yeah. Okay. Sorry. So in the population dynamics, so let's view these systems as a perturbation of just a population dynamics, which is how you'd view the system if you were in a kind of fixed dimension setting or like a low dimensional setting. And then we'll get to the role of the extra mean zero term. So if I look at this system where I'm just updating according to this generalization error, what ends up happening is in all of the examples I described, for instance, or a lot of parameter estimation problems that are kind of simple in some sense, you might expect that the function phi is low dimensional effectively, even though the empirical risk is a high dimensional function that's very complex. Okay. And so, for instance, we could assume that this function phi is just a function of some notion of your distance to the true parameter. Okay. The population really shouldn't care too much about the other directions. Maybe you have a radial term if you're working in full space. So in a spherical prior, we'll take something like this. And with a Gaussian prior in full space, for instance, we could look at something like a normalized inner product. Okay. So we're going to assume that our function phi is effectively low dimensional, and in this case, effectively one dimensional for the purposes of the talk. And for instance, in the spike tensor model or the tensor PCA problem, which we can use as a kind of running example, this phi is just of the form essentially m minus m to the k with some extra correction. So here's in matrix PCA, which is the case k equals to 2, you have something like this. And this x-axis here is m. So the correlation going from -1 to 1, or the normalized correlation going from -1 to 1. On the right-hand side, you have tensor PCA for a 3 tensor, let's say. Okay. And what you see is in these kinds of problems, there's a saddle point at the origin. So exactly when you have zero correlation, you have a saddle point, which maybe is going to be an obstruction to recovery, because you can realize that if you take a random initialization, you're going to typically start with correlation that's microscopic. Okay, so whereas I said the fixed dimensional intuition suggests that your stochastic gradient descent is just a perturbation of this dynamical system. This dynamical system gets stuck where you initialize, and like a short time asymptotics are only relevant if you start kind of away from the origin. So in order to make this more formal, we also have to assume something on the size of the noise, because if the noise is too small, then you're just ending up with this population dynamics. And if the noise is too large, then it might be doing something uninformative. Okay, so our assumptions on the size of the noise that we're going to be talking about are that this normalized thing, so by noise, I mean the loss minus its expectation, is well behaved in that it has like a high dimensional scaling. So its projection in the direction of this hidden parameter theta naught is much smaller than its norm. So in this case, we're thinking about, for instance, the projection in the direction of theta naught being order 1, whereas the norm of the gradient itself being order n, order root n typically. So in particular, a Gaussian vector in Rn fits this scaling relation. Okay, so this is kind of a high dimensional scaling where we're saying that once you subtract off this mean term, this is an uninformative landscape. It's not really, it has no reason to point you towards the true parameter anymore. Okay, and again, this is a setting that's satisfied by the kinds of problems I mentioned earlier. So for instance, in tensor PCA, your extra term is this Gaussian K tensor acting on x to the k. And in this case, it really is like just a Gaussian vector. In the one layer network with Gaussian features, you can see that your population is this kind of quantity where these are the Hermite coefficients of your activation function. And once you subtract that off, then L minus phi satisfies the kind of scaling relations I mentioned on the earlier slide. And in the binary Gaussian mixture model, again, similar situation. Okay. So this framework at least satisfies these kinds of one-dimensional recovery problems where we're just caring about the correlation with this hidden signal. Okay. So the kind of stochastic approximation or limiting ODE approach I was talking about, where you just send this extra mean zero term to 0, is valid in the regime where you're starting away from this saddle point at the origin. Okay. So if I start with any omega of 1 correlation, then I'm going to move pretty quickly with the population dynamics, right? Because it has some positive drift, in this case to the right-hand side, and in this case away from the origin. And as soon as it has a positive drift, I can do a kind of standard argument to argue that I have a law of large numbers. So my correlation to the truth is within a little of 1 distance of the correlation to the truth of this like population dynamics. This population dynamics, again, is just you're just following the dynamical system dictated by this simple one-dimensional function. Okay, so this is saying the low-dimensional intuition is really valid. Okay, and based on this, you end up with a system where you have a fixed point at the origin, which is unstable, for instance, and then an attractor at correlation 1. And in between these, you have a law of large numbers, even in this high dimensional regime, because you can project down and nothing goes wrong because things move quickly. But when you're near the saddle, the population dynamics is very slow. So because you're starting microscopically close to the origin. So this is the law of large numbers picture. If I start with some positive correlation of 1/2, you see these are repeated trajectories of stochastic gradient descent. They'll converge to the same trajectory, and that's given by the ODE that's given to you by the population loss. But if you start really close to the origin, and again, if I start with a random like Gaussian prior, then its correlation with a fixed vector is 1/√n typically. So I'm looking at a 1/√n neighborhood of the origin. Then the population dynamics is going to take a diverging amount of time to escape this small window and actually reach a region where it moves quickly. So even though I have this kind of law of large numbers on linear time scales, it's not telling me anything. I'm just staying fixed in when I look at this like correlation function. Okay, so I need to go beyond these kinds of short order 1 time scales. And so I want to kind of hone in on this unstable fixed point and the behavior there. How much time do I have?
I think it's like 5
Okay.
minutes.
So yeah, so in this regime where the population dynamics is slowed down, we need to kind of avoid sending n to infinity first and then looking at short time asymptotics. We have to hone in on the trade-offs between these two things. And in order to do that, so the consequence here is that if I draw x not randomly, then my correlation starts close to a saddle of phi. And in particular, most of the data is needed to be used. So most of the data I need is used already before I get to this kind of law of large numbers regime. Okay, so if you want to really understand the system, you also have to understand this first stage. And the question I want to ask is how much data is actually needed to escape this unstable saddle point in the origin. So to hone in on that, I'm going to define what I'll call an information exponent. And it's a notion of kind of the level of instability of the saddle point. Okay, so I'm just going to say it's k if the first non-zero derivative of this function phi at the origin is the kth one. Okay, so if k is 1, then there's not even a critical point there. It's not a saddle. And truly just the limiting ODE that you get is the truth. You quickly descend to correlation 1. So that's, for instance, the case with this single layer network with an activation function that's ReLU. Okay, so here you do quickly descend to the truth in this simple problem because there's no saddle point at your initialization. But suppose that we took like a f of x that's the absolute value of x. So this is a phase retrieval kind of problem. Then there is a saddle at the origin that's separating a kind of sign symmetry in the problem. And this slows the dynamics down because when you initialize, you're starting really close to this fat flat region. And so that we're going to call it k equals to 2 because it's the second derivative is non-zero. Okay. And you can have things, for instance, if I take the third Hermite coefficient as my activation function, which is a kind of bizarre thing to do, then I can have things, or a better example maybe is a tensor PCA with a 3 tensor. Then what I end up with is a higher order saddle point here. And so here I would say k equals to 3. Okay. And so the main result is that, a few examples. So for tensor PCA, the information exponent is exactly the order of the tensor. So as soon as you get beyond 2, this flatness is really severe, essentially. In the one-layer Gaussian network, the one-layer network with Gaussian features, it depends on the Hermite coefficients of the activation function. And in the binary mixture model, it's a k equals to 2 kind of problem. So you have some saddle, but it's a mild one. So the main result is this kind of classification of the time scales on which it takes to escape this saddle point for the stochastic gradient descent. Okay, so what you have is there's this, let's say alpha critical is this is the sample complexity. So the ratio of m over n that you really need to escape. And when k equals to 1, you just linear time is enough, as I said, because there's no like slowdown at the initialization. When k equals to 2, it's logarithmic, which you maybe guess from like a matrix PCA kind of intuition. It takes n log n time to get to the true eigenvector. And when k is at least 3, you have this polynomial slowdown. And so k is at least 3, this becomes polynomially large. Okay, and this corresponds to the kinds of thresholds that you have in terms of needing polynomially diverging signal to noise in like a tensor PCA problem. Okay, and so our main result is that if you take at least this much data, then the stochastic gradient descent with a good, well-tuned step size goes to 1. Its correlation goes to 1. And essentially this many steps up to like a log or 2 is necessary for the online stochastic gradient descent also. Okay, so without that many steps, it's really the instability is going to prevent it from leaving. And so here's a little simulation of a couple of like the first Hermite coefficient, second Hermite coefficient, and third Hermite coefficient used as activation functions in your single layer model. And you see that the timescales to recovery are completely different and they match what we expect. And I'll just end quickly with 2 warnings. in terms of the initialization, in terms of why things are even more subtle than just what I explained. So for instance, what I was saying was you initialize with a 1 on root n correlation, which is the typical start. So what if you started with something that's, sorry, this should be n to the minus zeta. So something that's microscopically close to the origin, but on a different order of magnitude. So whereas for the simpler k equals to 1 and k equals to 2 settings, that doesn't make much difference. When k is at least 3, this can change the polynomial in terms of how long it takes, okay? And what that means is if I start, say, on the other side, so with half probability, I start at minus 1 over square root n correlation instead of 1 over square root n correlation, right? A random initialization isn't going to pick a sign typically. Then it can actually take a much longer amount of time in this k at least 3 regime, because you first have to wait until you cross the y-axis. And for that, you're basically just doing a random walk. So you need to leverage the noise in your SGD, and there things slow down, and then you get to the other side. So in these kinds of problems, it could be that a random initialization half the time gives you one time scale to recovery, and half the time gives you a completely different time scale to recovery. And I expect that in higher dimensional problems where the phi depends on more variables, it could be that you have a whole host of different time scales depending on like the number of saddles you have to pass through. So I think there's a lot to explore in terms of these kinds of near saddle behaviors where the population dynamics itself is slowed down and the SGD itself should also be slowed down as a result. So I'll stop there.
Great questions for Reza. Maybe Song, if you want to get started.
So this is an extremely minor, like nitpicking question, but in your main theorem, when in the k at least 3 regime, is there some, like, are there kind of log terms hidden? So that log that shows up when k is 2, is it still there, but just kind of not making an important contribution, or does it really switch to being truly this polynomial?
No, so it should be truly it's like actually going to be a very sharp like number basically, which is given to you by the initialization, because once you have like, so the log is coming from a Gronwall type of thing where you have to like, you're getting some like exponential growth because it's and then in the k at least 3 case, it's like a higher order nonlinearity. So there's a very sharp time at which you recover depending on the value of the initialization. Okay. So I mean, like small oscillations in the initialization make big changes in the time scale. But if I fix an initialization, it'll be a very sharp time.
Yeah, I'm just also curious about, I guess this is when the likelihood or whatever is not one dimensional, but are there analogous results about escaping from saddle points, but where only a handful, you're in a high dimensional setting and there are only a small number of unstable directions? Yeah,
so I think that's an interesting question that, I mean, we're kind of trying to look into is, so the key thing here is that it's like a kind of escaping saddles with noise, but the initial data point, the initialization is also like dimension dependently close to the saddle itself. And so that trade-off in a, like, let's say a system where you have a cascade of 10 saddles would be an interesting question to understand and relevant to like other low dimensional but not one dimensional problems. So you might have a few directions that lead to a few saddles, and depending on which trajectory you take, you can get different timescales to recovery.
There are tens of papers on this single topic, escaping by saddle using Langevin dynamics.
But in high dimensions.
Michael Jordan said. And the other remark is that every single problem that you treated, there are sharper results available in the literature.
Yeah, so I would say like, we're not aiming to get sharp results in terms of like just algorithmic thresholds or things like that. And a lot of people have worked on these kinds of things for specific problems, for tons of things. I think the goal is really to understand like, what are the specifics of the escape from the saddle point in this regime where both your initialization is going close to the saddle and also your dimension is diverging.
Great. Okay, in the interest of time, I think we should thank Reza again and move on. So